such that N1 and N2 are both greater equal 3, and two double points such that their indices are opposite. There is an isotopy of, well, F1 to F1 prime such that the set of double points of F1 and F2, of F1 prime and F2, is the set of double points of the original maps without the two double points. So this is the embedding case. What about the immersion case? Okay. Or N1 is greater equal 2 and N3 is greater equal 3, then we require the pi 1 M without N1 is isomorphic to pi 1 M. So you can go one dimension lower. So what about the immersion case? Okay, so given two immersions of complementary dimensions, pi 1 M trivial is always such that M, what am I actually doing? Sorry. No, now I want to start with one immersion. One immersion of half the dimension such that M is greater equal 3 and two double points, well, distinct double points, such that their intersection numbers are opposite. Well, then there is a regular homotopy of F to F prime such that S2 of F prime is the set of double points of the original immersion with these 2 points removed, but now I'm looking at the unordered double point set. Yeah. Now I'm dealing with one map only, and what I remove is actually, I mean, the double points. The order doesn't matter there. It matters here. This will be important in, say, 15 minutes. I mean, look at this. The order is actually important. If the sign changes, the order is important. Even if the sign is not, it doesn't change, and the fundamental group of M is non-trivial. This is important. But what I remove are the actual double, the unordered double points. It's one map. Okay. idea of proof. Yeah. Okay, so what is the situation? Let me draw a picture which is somehow in every book. So let this be one double point. So this is x, this is y, just might be something else. So this is n2 and this is n1. So the idea is I can draw a curve from one double point to another in the first manifold, and then curve back in the second manifold. So what I want is to embed a disk here. So this is a sphere. If I manage to embed a disk which doesn't intersect these two manifolds except in this curve. So the interior must be free. It must intersect N1 and union N2 trivially. Then I can isolate one of the curves. Well, one of the curves, basically one of the manifolds across the other. Across the disk of the intersection. Yeah. And I mean, this sounds easy. This is actually what is the main bit. So embed a Whitney disk. Main bit is to achieve the following. So what I can certainly do is, if I start with two curves in R2, so let me call this C, naught, C naught prime. This is A, this is B. Well, I can find a smooth embedding of these two curves into this situation. Yeah. So I want to transfer this situation to a standard model. Yeah. So this is not a problem. Find an embedding of this inter M. Now, well, I want it to be somehow homeomorphism on its image. So I need to make it big enough so that the dimension match actually. So lemma, this is a lemma 6, 7 in Milner's notes on the H-cobordism theorem states the following. So I can extend the embedding of a neighborhood of this situation let me call it U, can extend the embedding can extend the embedding of the neighborhood of the curves. So in R2 actually to an embedding of U cross R and U Rn1 minus 1 cross 5 2 minus 1 through okay, so what's the problem about this with this actually? So again, I need a local situation to make sort of this. So I need somehow a local homeomorphism on its image. So I can't just map from R2 I have to make it big enough, first of all. And then the second condition is the image of the actual disk, the interior of the image of the disk should intersect N1 union N2 trivially. And this is, well, such that phi of B, the interior of the disk intersects N1 union N2 trivially. Yeah. So, and this is actually, I mean, this is the main work. This is this whole chapter 6 is about this lemma, actually. And now, I mean, once this situation is given, I have only to understand what happens on the U part, and this Euclidean contribution is just made to make it, to make it right and well. I mean, this lemma, for example, so what are the conditions? That the indices have opposite signs is somehow used here, and of course the dimension conditions. And why the dimension conditions? Because you're somehow using normal vector fields on the curve. You can embed, say, a neighborhood of the curve cross this Euclidean part into M, and so say, yeah, so you can embed this, but then you want to continue to extend it to the whole disk, and so this is only possible if this sphere you get here is contractible. So you have to extend it to a D2 and to an embedding of D2, and that's where this embedding theorem enters. So you need a map from D2, or there's a particular map from D2 into the manifold, and this is this can be made homotopic. No, you can find a homotopic map which will have an embedding. Why? Because the dimension of M is at least 5. This is this famous dimension restriction in all the surgery program. It works only from dimension 5 on. Well, I already removed this. So actually from dimension 6 and dimension 5 you need this requirement that pi 1 of M without the lower dimensional manifold is isomorphic to pi 1 of M. So, but the dimension 5 enters here. You manage by using some normal fields to achieve this, but not on the whole disk, only up to, well, some neighborhood across this Euclidean part, and then you want to extend, and then you need this condition.